Good morning, class. We're going to be talking about structural analysis today. So structural analysis aids the structural engineer in designing, evaluating, and verifying the structural integrity of the structures and mechanisms on the spacecraft. So let's define what structural integrity means. It's a way of quantifying the safety of a structure to survive. It's quantified by something called a factor of safety, which is a ratio of the failure load over the design load, or analogously, it's the failure stress over the design stress. Load and stress are just scaled by the cross-sectional area. We want all of our components in the spacecraft to adhere to the requirement of a factor of safety above 1.4. Factor of safety is something that we can get as a result of our analysis. I'll talk about different analysis techniques later on in the lecture. So I took these tables from NASA's standard document for defining design and test factors of safety. So you'll see for metallic structures, there is an ultimate design factor of 1.4 and a yield design factor of 1. And then for fasteners and preloaded joints, it's a little different. You'll notice that for different materials and for different functional parts, the safety factor requirements are different. So just make sure that, well, our CubeSat isn't going to be that complex in the types of components inside, but just make sure that you're aware that different components, different degrees for safety of factor of safety. And then here we have a question. The factor of safety is very commonly 2. Why are bridges designed with a much higher safety factor of safety than aircraft are? Sorry, not to the question, to me, keep like switching up factor and safety. So the explanation for that question is, buildings commonly use a factor of safety of 2 for each structural member. The value for buildings is relatively low because the loads are well understood and most structures are redundant. Pressure vessels use 3.5 to 4, automobiles use 3, aircraft and spacecraft use 1.2 to 3, depending on the application of materials. The field of aerospace engineering uses generally lower design factors because the costs associated with structural weight are high. For example, an aircraft with an overall safety factor of 5 would probably be too heavy to get off the ground. Remember that factor of safety can be cranked up by adding more mass to a system. So that's why we keep it low. This low design factor is why aerospace parts and materials are subject to very stringent quality control and strict preventative maintenance schedules to help ensure reliability. They usually apply safety factors 1.5, but for a pressurized fuselage, it is 2.0, and for main landing gear structures, it is often 1.25. So the different components in a structural analysis that we would have to extract or define are failure loads, area, and the design stress. So failure loads are something you have to quantify when you're thinking about all the loads that could be applied to the spacecraft. And then stress, as defined by load over area, that area is defined by the geometry of the part that you've designed. So let's break down those 3 components. Design stress is typically defined by a yield and an ultimate strength number associated with the material. There are 2 different types of stress. So yield stress is the amount of stress that an object needs to experience for it to be permanently deformed. And that would be this picture right here. Ultimate stress is the maximum stress that a material can withstand while being stretched or pulled before breaking. So that's that final image here where there's a fracture. So I'm going to explain this stress strain plot here Real quick, strain is how an object deforms when forces are applied to it. So typically, a material has a region called elastic deformation, where you have your material structural component with no force on it. This is its original shape. At some point, you're going to apply some force to it, some stress, and it's going to deform. But in this regime, the material component can return back to this original shape. Past that point, there's going to be yielding, where the material has plastic deformation or plastic strain, and it cannot return to its original shape. And then, like we were talking about ultimate strength comes after yield strength. And you notice that phenomenon when this necking or fracture occurs. For some common materials, remember this slide. Now you know why there's this differentiation between a yield and an ultimate strength number. So typically the ultimate strength is at a higher rating than the yield strength. For aluminum, you have to apply 276 megapascals of pressure to get the component to yield. And so then you apply, 46 more megapascals, and then that component fails. Titanium is the strongest of these materials that we have listed commonly for spacecraft. But as we discussed last time, there's a reason why not many parts are made out of titanium, because of the extreme cost. In most cases, aluminum is good enough. All right, so to define critical loads, we obtain or estimate loads. This can be done by looking up loads in reference books, like here, where I'm going to explain where I've taken these numbers. You can ask other groups to determine loads or guesstimate for the purposes of starting analysis. Some loads are just not known beforehand, so you can do back of the envelope calculations. For example, remember SMAP, the Soil Moisture Active Passive Satellite? It was this huge boom with that large antenna. So you can do a very simple calculation of like, what is the mass of that huge antenna? And how does it resonate, or what kind of accelerations will it experience? And then you've got an F equals MA kind of guesstimate for that kind of loading. The two loads that we're most preoccupied, at least stated here, we want our structure to withstand 1200 newtons between the two XY planes applied in the Z direction. We got this from the NASA CSLI requirements. And then the other requirement is the CubeSat shall be capable of withstanding a force of 1320 newtons across all load points equally in the Z direction, provided by the NanoRacks deployer document. Now that I'm looking at these two requirements, there's one requirement that supersedes the other. So in spacecraft design, we typically like to be more conservative. So in this case, this requirement of 1320 newtons is a more stringent or more rigorous requirement compared to the CSLI requirement. So we would design to this requirement. These tables that you're seeing here are different loads. So I've taken all of these tables from NanoRacks, where this top table is a profile of different accelerations in X, Y, and Z. And typically they are quantified in Gs. So if you wanted to convert this to meters per second squared, you multiply by 9.81. And these accelerations are experienced during launch. There is also angular acceleration that can be translated into the types of torques that you'll see in the spacecraft, and that's going to translate to a torsional load in your spacecraft. There are also other loads like vibrational tests and profiles that you have to test to. You can either do this through finite element analysis or through an actual physical test. Here is a shock profile. Here's a thermal load environment. Yeah. Okay. Now I want to talk about points of failure, and this is dictated by geometry typically. You can find points of failure as usually being the weakest link along the critical load. This can be joints, nuts, slender beams, what have you. There is this case analysis of a SpaceX rocket disintegrating during ascent. And then NASA was interested in why it failed. So here is a screenshot of the component that ultimately failed and the subsystem that, the context for that component. So this eye of a bolt failed. And because this failed, which was here, this tank, I believe, exploded. So I'm going to read from the report. It is credible the initiating cause was the failure of the axial strut supporting a COPV, which in turn liberated the aforementioned COPV, and which in turn ruptured the gaseous helium plumbing system within the stage 2 liquid oxygen tank. It is credible that the COPV became liberated when a threaded cast stainless steel eye bolt, aka rod end, here, of the COPV's axial support strut broke under ascent loads, allowing the COPV to break free from its mount, allowing it to accelerate due to its buoyancy to impact the liquid oxygen dome at the top of the liquid oxygen tank with great force. So this is the failure report for this rocket blowing up. It's not always clear exactly why things fail because you reach the components after they've blown up and disintegrated and they're scattered. So it's kind of like this forensic investigation to see what could have happened based off of the pieces that you see on the ground. Then we'll look at a little case study where at NASA Kennedy, they have come up with this innovative jack screw that prevents the failure. It's like a secondary precautionary measure to prevent failures. So a little bit about that. More than 4,000 jack screws were in use around Kennedy Space Center during the space shuttle era. NASA used some of these jack screws on critical hardware. Thus, a fail-safe, continue-to-operate design was needed to mitigate the possibility of a catastrophic event in case of failure. A conventional jack screw contained only one nut made of a material softer than that of the threaded shaft. With prolonged use, the threads in the nut would wear away. If not inspected and replaced after excessive wear, the nut eventually failed. Kennedy Space Center's fail-safe concept for machine jack screws incorporated a redundant follower nut that would begin to bear the axial jack load on the failure of the primary nut. Unlike the case of a conventional jack screw, it was not necessary to relieve the load to measure axial play or disassemble the nut from the threaded shaft to inspect the nut for wear. Instead, wear could be determined by measuring the axial gap between the primary nut and the follower nut. So if this component starts to hug the follower nut, then you know that the primary nut has failed. Additionally, electronic and mechanical wear indicators were used to monitor the gap between operation or assist during inspection. These devices would be designed to generate a warning when the thread was worn to a predetermined thickness. The fail-safe, continue-to-operate design concept offered an alternative for preventing catastrophic failures in jack screws, which were used widely in aeronautical, aerospace, and industrial applications. Okay, so now we'll talk about verification methods. So ways to verify that your design isn't going to fail prior to launch and mission operations. So this is taken from, I think, the same NASA standard documentation. This is a just verbatim section on verification methods. So the tests that you can conduct fall into 3 basic categories. Tests to verify the strength of the design, so qualification. You can think of physical tests, tests to verify strength models. You can think of this as math models. And then tests to screen for workmanship and material defects in the flight articles. This is more a quality assurance thing in the manufacturing or while you're doing acceptance or proof. Okay, strength verification tests are normally static load tests covering critical load conditions in 3 orthogonal axes. Strength model verification is normally performed as a part of the strength verification testing. Strength model verification may not be required if the load path is easily determined and straightforward and the flight loads are well characterized. Structural designs generally should be verified by analysis and by either prototype or protoflight strength testing. For metallic structures only, it may be permissible to verify structural integrity by analysis alone without strength testing. So one of the questions was, why can metallic structures be verified solely through analysis when other structures need strength testing to verify their designs? So metallic structures are relatively well understood, so we feel confident that our models are good representations of what a physical part would behave like. Okay.
Machine.
So now we're going to see videos of how these tests are actually done. This is a tension test where a sample...
In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared.
The sample is loaded into this
Then he selects all necessary testing parameters on the control computer. The gauge length can be measured throughout the whole tensile test.
These lines
The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters.
So those lines let you keep track of the elongation of the sample. Then you're applying load.
The material behavior can best be...
And you have a machine that's measuring the load as you're applying load. It's reactive force. You're also measuring the elongation of the sample over time. At some point, at that point, the sample starts to yield, and then you keep applying load to see where the ultimate strength fails. So I'll let this play out. This is a lab that I did as an undergrad, where we actually loaded these samples in. And then we had to analyze the behavior of stress and strain of samples. Almost there. So for this particular sample, the yields and the, oh, there's necking. Yield and the ultimate strength are quite far apart. Actually, no, that's not a good analysis. I would say that the reason for this really long elongation is because the material is ductile. Anyway, failure just happened where you suddenly see zero load applied because the component is no longer connected to each other. Okay, so that was axial tension loading. Let's look at axial compression loading.
Force evenly applied to both ends of the specimen. compressing forces are now being applied to the specimen. When wood is stressed in compression parallel to grain, each wood fiber acts as an individual hollow column with some support from the neighboring fibers. At failure, a number of fibers buckle simultaneously, producing a local reduction of strength and shows an initial linear force displacement relationship up to the point in which fiber buckling occurs at around 370
That's what compression looks like.
meters.
Same kind
At
of
this
machine
point,
setup.
buckling instability is triggered and a sharp reduction in the compressive capacity of
Okay,
the specific force evenly applied to both ends of.
enough. And then there are fatigue tests, which are cyclic loading. So you'll see here that there's a sample that's being stretched, then compressed. And every sine wave of that loading counts as a cycle. And you want to see at that minimum load and maximum load over how many cycles will the specimen fail. Fatigue failures can be identified by cracks that start to show up. Over more cycles, that crack starts to propagate or get larger until there's a complete fracture. And then vibration testing. Let's see a video of what that setup looks like. There are different acceleration profiles, so like a max acceleration at a certain frequency that is desired for vibration testing. So there are these vibration tables that oscillate and provide that kind of acceleration and frequency. And then there's the structural component of interest. Yeah. So that's what those tests look like and all the equipment around it. Now let's get into hand calculations. So strength model verification may not be required if the load path is easily determined and straightforward, and the flight loads are well characterized. So in the case that we have easily determined and straightforward flight loads, then we can do calculations like this, where an axial or shear stress calculation can be determined by this sigma is equal to, or stress is equal to force over area. Or if you rearrange the equation, force is equal to the stress times the area. Your factor of safety is failure stress over design stress. So your design stress is what you actually plug in, or your design load, F, is what you plug in. Your design stress, if you know that number, you can plug in, although load is easier to physically measure. And then your failure stress, which is the other unknown in this equation, is derived from material properties. If you know design stress and failure stress, you can calculate factor of safety. And then you just do a binary check. If factor of safety is above 1.4, then yay. If factor of safety is below 1.4, then nay. You redesign either the material or the cross-sectional area of the component. For buckling, the equation for load and stress is different. So the critical load in this case is a relationship between Young's modulus, the moment of inertia of the component, and the length of the slender member. So we'll look at this over here. This is for boundary conditions that a slender member the ends are held in place. They're allowed to displace vertically along the direction of the load. But you can think of this like the CubeSat rails, which are being compressed at 1320 newtons. So the critical load, let's walk through the design activity of analyzing its factor of safety. So in this case, from the material properties, we have E, we know the parts geometry I and L, so we can figure out what the failure load is. So we have that part of the equation. And then we know from, say, like nanoracks, what the design load is going to be, 1320 newtons, so we can get the factor of safety. So then, same process, we know that what the design load is or what the factor of safety is. So I'm showing you a different way to formulate the factor of safety equation. You can take this inequality any way you want, where like factor of safety is less than 1.4, or if you rearrange the equation, is the design load less than the failure load divided by the factor of safety? If so, yay. If the design load you experience is greater than the failure load over the factor of safety, then nay. Redesign the material or cross-sectional area, or for this particular loading condition, you can add a strut. A strut is a supporting slender member, and the way that a strut can affect your critical or failure load is, let's say you put a strut here or here, then your effective length is reduced and your critical load equation scales down. So it brings the critical load up if you add a strut in. Okay, let's talk about beam stiffness. So you can think of this loading situation as like the SMAP spacecraft, where here's SMAP stowed, but if you start to deploy the boom and then you go into mission operations and you deploy your reflector, SMAP is spinning around. So you want to make sure that this boom survives the kind of load that the reflector imposes. This is like measuring the deflection of a beam, a freestanding beam, where that load is the acceleration on that reflector mass. You can figure out the maximum deflection that this boom can withstand by implying this load times the length cubed over 3 of the Young's modulus times the inertia. So here's another way of formulating whether your design is safe. Instead of using failure load or stress, you can use the deflection. So if you know or can measure the amount of deflection, here's this equation: design deflection is equal to the failure deflection over factor of safety. You'll see here that load and deflection are linearly correlated with each other, which is why you can do this, this swap in or replacement. It's exactly linearly correlated. So load, stress is going to have the same ratio as deflection. So then you can find failure deflection. If your design deflection is less than your failure deflection over factor of safety, then yay. If it's greater, then gotta redesign. Maybe reduce that load by having a smaller antenna, or beef up that boom's cross-sectional area, or make it out of titanium. Okay, for vibe testing, you can also do a hand calculation where the vibration can be approximated as some kind of acceleration load. This is the equation where the acceleration load is defined by the square root of the frequency, the input acceleration at that spectral density. Anyway, it's an approximation, and you can use this equation to find the approximate stress from vibration as mg over I, which is the inertia. And this is Planetary Resources showing us how they vibration test their spacecraft. to that table. From the few slides that I've presented, the main point is that there are different loading conditions. There are different equations that you use. In the end, you want to get a factor of safety one way or another, whether you put a ratio of load or stress or deflection. You can use those ratios and still get a factor of safety. Okay. The last load that I'll talk about are thermal loads. So you'll see thermal loads, for example, on railway tracks where these long, slender beams are expanded during like a summer day when it heats up. When that length, that difference in length is not accounted for, then you'll get behavior like this where the rails start to buckle. Ways to prevent that can be seen on bridges, for example, where these joints allow for some expansion to occur. But if you don't have the ability to accommodate this expansion, this difference in length from expansion results in some axial loading, some force. You can calculate this by, you have your coefficient of thermal expansion, alpha. You know what your temperature change is going to be, and you know the length of your slender member. So you know the total length difference you'll have. And then you can use this equation to find the amount of stress on that member given your Young's modulus times that difference in length. So once you have stress, again, you have your failure stress, which you just found. No, sorry, you have your design stress, which you just found, and then your failure stress is given from your material properties. That gives you factor of safety. And then again, do the binary check. Factor of safety greater than 1.4, yay. Less than 1.4, redesign. Okay, finite element analysis. So finite element analysis is the computational version to what we just talked about. All the hand calculations we discussed prior to this slide were macro interactions. You think of the component in test as one piece. Those hand calculations are sufficient if the load path is easily determined and straightforward and the flight loads are well characterized, right? But what if we had a structural component with a more complex shape? Or the load path was not directly axial or shear or torsional? What if there are multiple forces or boundary conditions? Then we have to look at how micro interactions sum up into a macro response. So finite element analyses, the advantages are use differential equations, you can apply boundary conditions in complex shapes, and you can apply finite element methods to stress analysis, which is what our particular interest is. But you can also use it for fluid mechanics, heat transfer, diffusion, vibrations, electrical and magnetic fields. So here you'll see finite element analysis results for a truss structure where that original truss is in that gray shadow, but then this rainbow mesh is showing us the reaction where blue is less stress and red is more stress. And then here you'll see a car's response to a collision, an asymmetrical collision. It would probably crush somewhat like that. You can also use it for biomechanics. So here you'll see a knee joint with the cartilage and bone meshed up. And see what the stress is like on these different ligaments. Here on the bottom is a electrical and magnetic, let's see, what is it? It's so here is a finite element mesh to find a solution to the magnetic problem. The colors indicate that different material properties for each zone. So there's this blue versus gray versus brown that are different materials. Although the geometry may seem simple, it would be very challenging to calculate the magnetic field for this setup without finite element analysis using equations alone. This is the solution to this magnetic field problem, which this is a solution involving a cylindrically shaped magnetic field. The ferromagnetic cylindrical part is shielding the area inside the cylinder. So you see the magnetic field being deflected. And the colors represent the amplitude of the magnetic flux density. Anyway, I thought this would be a good summary of why finite element analysis is used, the different applications and why it could be useful. Oh, and then the question, this type of computer modeling, is it something in-house systems can do, or are models sent out for supercomputing? So the structural lab has you downloading software on your own computer and doing the analysis on your personal computer. I think that's pretty incredible that you can have these powerful tools at hand. There can be models that are really computationally intensive, but I mean, if you're doing that kind of work, you're probably at a well-funded, well-resourced institution. So hopefully you can use like supercomputers there. But for our purposes, we have this tool at hand. Okay, how does finite element analysis work? So fundamentally, it's taking a geometry, whether it's in 1D, 2D, or 3D, and it's dividing that body into a finite number of pieces called elements. Thus, finite element analysis. There are different types of ways that you can cut up a geometry. If it's in 1D, you can do beam. 2D, there are different shell patterns. And then a solid, you'll see these different volume cubes. Next, you apply assumptions on the behavior of the elements. And this kind of behavior can be an interpolation or an approximation of first principles. And the assumptions are a function of the nodes. So earlier you saw there are the elements. Every element has a node at a vertex. At these vertices, you have approximations of the real continuous behavior. So this can be interpolated, linearly interpolated, and roughly approximated. Then there are other discretization methods, like if you use a quadratic model, then the interpolation gets a little closer to the real thing. And then finally, you apply an algebraic system of equations for unknown node values, which approximates the continuous solution for a bar element. So let's just look at this simple example. You have these boundary conditions for these two nodes that represent a bar. The differential equation that dictates the way these nodes interact with each other is given here, and then the boundary conditions are here, and they're applied at the nodes. And you get something like this, where you have your boundary conditions, you have your system of equations. I'm not going to go into them, but some of the equations should look familiar, given we just did hand calcs. But these micro interactions, like each line of equations represents some node that's being acting on another node. So like these are neighboring nodes, for example. Reaction, reaction. But eventually you can sum up all of these little micro interactions into a final result, into a macro response. I won't go in too deep into the innards, but to use this software analysis, you'll get a result like this. So you'll apply a force For example, this case, we applied 1200 newtons in the Z direction on that face, normal direction. And then we got a stress result or distribution like this. And then you can convert that stress to a factor of safety within that software, and it'll automatically calculate for you. The factor of safety for a 1200 Newton load is 4.98. And then Kenny-san did this analysis, I think. Anyway, he found that the maximum failure load was found to be 6 kilonewtons, which is approximately 2,700 toilet paper rolls. And he did this analysis when pandemic was like just ramping up. I thought that was a funny result. Okay. Lastly, the last question I did not get to answer in the process of the slides is, if the CubeSat is found to not fit in the launcher, but meets all the requirements, does it get sent back, or does the launch provider modify things? So if the CubeSat is found to not fit in the launcher, then that's straight up not meeting a requirement, and you could very well be at risk of getting it sent back. Many launch providers do not modify your design for you, so they wouldn't mill your frame down. You would probably have to travel to the launch provider to modify things and have to do resulting analyses to make sure that your factor of safety is still sufficient. So it's not a good look if your CubeSat is found not to fit in the launcher. Okay, I'm done with today's lecture.